is going to be to revisit maximum likelihood estimation. I'm sure it's your favorite by now, right? Actually, I do think it's kind of cool stuff. But what we're going to do is we're going to look at it, for regression. So before I get into this too deep, let me just make sure that I'm actually recording here, because this is going to be one of those presentations I really don't want to do 2 times. So I'm going to take about a little bit of time here. Make sure that I have, yeah, okay. See, so many things have happened behind the scenes that you guys don't know about. There's been one video that I posted for about 50 minutes and I realized that I had the audio turned off, so I had to redo it. So I'm going to be very, very, very careful that doesn't happen again. So guys, ultimately what drives all this is when the form of the probability distribution I don't like that setting, man. Let's go try this. Is known. The estimators of beta 0, beta 1, and sigma squared can be approximated using maximum likelihood estimation. So that's where we're headed with again with this this video. So again, I'm not happy with the size here. Let me see if I can make something happen a little bit better. Okay, let's try this. So ultimately, guys, what our MLE does, it chooses the parameter estimates and we'll just call those beta hat 0, beta sub 0 hat, beta sub 1 hat, and sigma squared hat. These are used to estimate the parameters that are most consistent with our data. So in other words, MLEs kind of work in reverse in that we look at our data first and then kind of work backwards, trying to find the parameters, or at least the parameter estimates that seem to best fit our data. Now I want to revisit, it's been a while since we've actually talked about MLE, so I want to look at an example. So let's say that we have n equal 3 observations. From a normal distribution. With population standard deviation known, let's just let this be 5. So let's say our observations, x1, let's say is 10, x2 is equal to 12, and x3 is equal to, oh, I don't know, what do we need here? Let's keep it where, say equal to 14. Now, the underlying question which is more likely? To have drawn this data from a distribution with mean equal to 9, or a mean equal to 13. So what we can do is we can just look at a couple of illustrations here. So guys, if we have a mean equal to 9, and our data was, what, 10, 12, 14? Well, that could happen. Certainly could happen. And if we have a normal distribution with a mean of 13, again, what we're doing here, we're setting, again, the variance is 25. So we have 10 and 12 and 14. Now, guys, y'all have to agree with me that just based on probability, based on likelihood, that this distribution right here was more likely. So that's going to be my bet. But my question is there a better choice for mu? When you force me, well, it didn't force me, but when the situation is given to me where I'm forced to choose between mu equal 9 and mu equal 13, well, I'm clearly going to go with mu equal 13 because it just seems to make more sense. Now, let's just recall that maximum likelihood, so recall, maximum likelihood estimation uses either the mass or the density function. In this situation, since we're looking at the normal distribution, we're going to have the density, uses the density of the probability density function at a particular y sub I. So ultimately, guys, what we've got a particular mean y sub I. The density of a particular point would be basically the height of the line, and the observation is more likely. What happened here? Oh, that's not cool. I have no idea why that happened. Huh, okay. So if we have an x sub I where the density is the height of that versus an x sub j, which is further located in the tail, then this density is going to be higher, and it's reasonable to say that it's more likely to get that observation with a particular mean, in this case of y sub I. So what I want to do here is get a little more mathematical with it. So again, we've got an assumption that the distribution has a standard deviation equal to 5. So guys, we all remember that the probability density function of the normal distribution is, if you don't remember this, you need to. Is this. And if we look at a specific case where the variance is 25, then we get 1 5 square root of 2 pi e to the minus 1/2 x minus mu quantity squared over 25. All right. Now, I want to investigate these measurements a little bit more, and I want to create a density table. I don't know. And what I actually want to do is I want to go back to this problem that we're working with, and we looked at mu equal 9, and I think we looked, I forget, was it 13? Is that what we looked at? Yeah, 13. 13. And our observations were 10, 12, and 14. Now, it's kind of a cool feature that we have in R that can calculate these densities for us, and it's called D norm, D chi-squared, D whatever it may be, whatever distribution may be. So what I'd like to do is now go to R, and again, what I'm going to use here, the D norm. So, you know, I want you to get kind of used to using this help function because it's extremely helpful, and I use it all the time. So if we use, you know, D norm, you can see that there are a variety of forms here. Well, what I want to do is I want to find the density of the function at a particular value, given a particular mean and a standard deviation. So I'm going to have to set log equal false. So guys, I will go, in this case, I'll go D norm at a value of 10 with a mean of 9 and standard deviation equal to 5. So in this case, I get 0.0782. All right, next thing I want to do is calculate the value for 12. And I get 0.06. 6642. And of course now I want to do for 14 with a mean of 9, standard deviation of standard deviation of 5. So in this case I get 0.0484. All right, next thing I want to do is I want to do the same thing for 13. So D norm for 10, but having a mean of 13, standard deviation of 5, I get 0.0066. Interesting. D norm, value of 12, standard deviation of mean 13, standard deviation 5, so here I get 0.0782. And then I get density value 14, mean 13, standard deviation 5. I get 0.0782 again. And that makes complete sense because you know, 12 and 14 are 1 unit to the left and right, if you will, of 13. So guys, what I can do now is I can take the density for 10. I'm sorry, density for mu of 9. I think I can do that. I'm not sure if I can put a... so that's going to be the product of D norm 10, 9, 5 times D norm 12, 9, 5 times D norm 14, 9, 5. So guys, remember from since we're dealing with independent and identically distributed variables, random variables, we can multiply the probabilities. So for that value, I get 0.00025, and I can go density mu 13. And I get a density mu of 13, which is almost double that of the density when the mu is equal to 9. So guys, let's go back to the chalkboard, and what I did is wrote these down. So the density here would be the product of these values. So basically I equal 1 to 3, and the product of these values. And again, this had a higher density, so it's more believable that based on our data that the mean was equal to 13. Well, so mu equal 13 as the largest product of densities. So it's most likely considering only the values of 9 and 13. And ultimately what this gives us a measure of consistency. Of the parameter value. The only two that we considered was mu equal 9 and mu equal 13 with our sample data. Okay. Now, clearly there are other values of mean, and so kind of lost my train of thought here. Okay, so clearly mu could be, is not restricted to being 9 or 13, so considerations for mu could be essentially could be any real number. So what I want to do now is I want to completely change gears and look at the regression model and the estimates of the parameter based on maximum likelihood estimation. So the concepts from before. To estimate which is more likely. Mu equal 9, mu equal 13. Can carry over to the estimation of the regression coefficients. And guys, up to now, regression coefficients we've pretty much focused on beta 0, beta 1, but now we've got this other estimate that we also want to be able to investigate. So let's set up the problem. So assumptions. We're going to say that each y sub I is normally distributed with mean equal to, let's say u sub I is equal to beta 0 plus beta 1 x sub I. And we'll say that our standard deviation is equal to sigma. So now ultimately what we got going on here is for each y sub I, again we have these different levels, and we predict with our model. This is so hard to draw. Please forgive me for the ugly drawings, but these things are crazy to draw. So for each y sub I, the mean response is the value we get by inputting the level x sub I into our model. So the main response for each y, and then we're going to assume that standard deviation is constant, so the variation within these distributions doesn't do anything wacky on us. Okay, so let's start an example, and I want to set my standard deviation here, and let's just set it to something really cool and easy for standard deviation equal to 3. Now what I want to do is I want to determine the likelihood that beta 0 equal, let's make it easy on ourselves. Yeah, that's cool. Given our data, in 30, 10. So guys, these are our measurements. This is our data. So we want to determine the likelihood that this model is the best fit for this data. All right, guys, so what I want to do first of all is kind of organize my work. So I've got let's see what space. I'm gonna need that out here. Ultimately, guys, what I'm doing is I'm trying to get everything on one page. All right, so we know the mean response. Make sure you hit them off of the pass. The mean response for each observation. So mu sub 1 is going to be 0 plus 0.5 times 20. And this is equal to 10. So the mean response for the second is going to be 0 plus 0.5 times 55. And the mean response for the third observation is going to be 0 plus 0.5 times 30, which I hope is equal to 15. Now, what we can do here, well, I'll tell you what, let's go back and now I want to play, and I want to create the density of each one of these. So this is going to be the density for each one. So remember that the likelihood function, given that beta 0 equals 0, beta 1 is equal to 0.5, and sigma squared is equal to 25. No, that's not right, is it? We chose 3. So it's equal to 9. Is going to be the product of our densities. So what we need to be able to do is go back into R and calculate the densities for probability density function for the probability distribution, and we can get the likelihood that these that this data came from the distribution with these parameter values. So let's get out of this, calculate some densities. So the first density I want to look at is let's see, normal distribution. So a value of 10. I'm sorry, a value of 20. If our mean is 10, and our standard deviation is 3. And I want to look at observation of 55. Mean of 10, standard deviation of 3, and d-norm of 30. Mean of okay guys, forget that. I did that wrong. Let's do this over. So the density for 20 is d-norm. Our observation is 20 from a mean of 10, standard deviation of 3. Our goodness gracious. Okay, wow. Guys, I promise you I can. All right, so we got 20. This is actually getting humorous. 10, 3. Density of our 55 is d-norm. 55 coming from a mean of 27.5 with a variance of 3, our standard deviation of 3. And our density for 30 is d-norm. 30, mean of 15, standard deviation of 3. So we can get each of these, if dynasty, am I seriously doing that? Okay, guys, all right, we just had a family show up, so that's why I'm kind of, so the dynasty, 20, oh wow, is 0.00051. All right, and density of 55 is, wow, extremely small, 7.5 times 10 to the negative 20th. And the density for 30, hopefully I spelled that correctly, is let's say 5 times 10 to the negative 7. So guys, we can get our product here. We can get our total density. Spell it correctly, just so you know I'm not complete bozo. So density 20 times density of 55 times density of 30 gives us our likelihood of getting our data if the parameter values are 0.5 and 9. So our total density is extremely small. So let's go back to the blackboard. So you can see that I filled in the densities and our total density, so the total likelihood given our x sub 1, y1, x sub 2, y2, and x sub 3, y3, coming from beta 0 equals 0, beta 1 equal 0.5, and sigma square equal 9. Let's just say not likely. And really, if we investigate this further, it actually makes complete and total sense. Because if we have our levels of 20 and 30 and 55, and we have our model. So if we just, what I want to do is let's just investigate, for example, this one right here, and I want to rotate it. Well, no, let's just keep it here. I'll just do my best to draw a normal distribution. So pretend this goes through and the mean response is right here, and pretend that's straight down. Well, the observation we get here for y, and I forget, I'll have to go back and look at it, for 30, what was it? When x is equal to 30, we got a y value of 10. But the mean response, we came up with there for 30 to be 15. So let's go again, look at this. For our first, second, and third order pairs, our mean response was 10, 27.5, and 15. But our actual y values were 5, 12, and 10. Notice each of these were overestimated by the means of the distribution. So what I'm asking you is if each distribution, if it's so hard to do, I really challenge y'all to do this. If each distribution, which has a mean, which lies on this line, and we get a distribution here, and a distribution here, and a distribution here, I'm sorry, not a distribution, we get sample data. So this would be our y sub 1, which was, again, 5. And our mean right here was 10. And we got our y sub 2 was 12. But the mean response was 27.5. And here we got a sample data equal to 10, so we had a mean response equal to 15. So in each of these cases, our mean has overestimated. Wouldn't it make a lot more sense that there's probably a better estimate, something that's more likely with different parameter values? There we go again. Well, that's more likely. So guys, as you might imagine, what we're going to do now is we're going to turn it into kind of more mathematical. So, you know, we could try many different values. So we could drive ourselves crazy investigating the likelihood for various beta zeros, beta 1, given that sigma is equal to 3. All right, so what we're going to do is we're going to get this and turn it in mathematical, to get this more mathematical. So guys, we know that the expected value of our y sub i's can be found by our regression model. And we also know that the variance of our y sub i's is given as sigma squared. All right. So guys, we can find the density at each sub I, if you will. It's probably horrible notation, but yeah, let's put all this in 1. All right. So from the previous density function for the normal distribution, notice that we've just replaced, this has been, which typically we have x minus mu over sigma quantity squared. We've just replaced our observation y sub I minus its mean. All right, guys, so let's take this somewhere. We know, therefore, that the likelihood function, or you better know that the likelihood function in general, so the likelihood given beta 0, 1, sigma squared is going to be the product from I equal 1 to n, 1 over sigma squared of 2 pi e to the, let's see if we can clean this up a little bit. What should I do? 1 over sigma squared. Okay, let's do this. Yeah, this is good. All right, guys. Clearly, we can clean all this up. Take the product of all the stuff on the bottom. So we get 1 over 2 pi sigma mean over 2 e to the minus 1 over 2 sigma squared. And since we're multiplying, we add our exponents. quantity squared. So guys, that's the monster, the beast that we're going to look at for maximum likelihood estimation. Now, what we're going to end up with is we're going to end up with beta hat 0 is going to be an estimate. Really kind of course, beta 0. And beta hat 1 is going to be an estimate of beta 1. And of course, it's going to be an estimate of sigma squared. And where typically what you see here I'll tell you what, let's give it this form right here. And if you solve simultaneously, this is actually what you get. Now, there's a problem with this. And the problem is this is a biased estimator. And it's also not consistent at all with what I taught you in the previous lecture, where we typically, if we want to estimate sigma squared, we will use the mean square error. This is unbiased. You guys remember we divide out by degrees of freedom at -2, accounting for the fact that beta 1 and beta 2, I'm sorry, beta 0, beta 1 have been used in the estimation of the mean response at each y. So again, this is unbiased, and that's what we really like to have. But arithmetically, work this out. This is what you're going to get. All right, gang. So guys, what we do is we take the likelihood function. Hopefully you're playing along with me here and you know what's coming up next. And what do? What's the next step? Take the natural log, because it turns out it is much easier to differentiate than most likelihood functions. So if we take the natural log of the likelihood function, we're going to get negative n over 2, natural log of 2 pi. If you do this long enough, this is one of those things that you just remember. And we end up with this. Is that supposed to be sigma squared there, or I think that's just supposed to be, no, Doug. Yes, okay. All right, guys, so next thing we would do, you tell me. I wish I could call you out on this one, but kind of impossible. What's the next thing we do? take the partials. And set equal to 0. So guys, what we would do, take the partial of L with respect to beta 0, set it equal to 0. Take the partial of L with respect to beta 1, set it equal to 0. And take the partial of L with respect to sigma squared, set it to equal to 0, and solve simultaneously. Now, I don't think I'm going to do that. I mean, those kind of, well, I'll tell you what, I can actually do it pretty quickly, probably about 15 minutes if we've got some time. We're 48 minutes on this one, so no, I don't want this to go. Okay, so guys, let's this actually I guess we're done. So let's end.